Electron configurations. Let's start by looking at the full electron configuration of the magnesium atom. The atomic number of magnesium is 12. That means it has 12 protons. It's a neutral atom, so it must have the same number of electrons too. So we're starting with 12 electrons. So here's the electron configuration for the magnesium atom. We start with the lowest energy orbitals first, which is the 1s. The number at the start, that 1, that tells you the principal quantum number or the number of the energy level. Next, the s or the p or the d or the f, that tells you the orbital. And then we have the number there, that tells you the number of electrons in this orbital. So that's principal quantum number 1, an s orbital with 2 electrons in it. Next we have a second energy level, an s orbital containing 2 electrons. Next we're in the same main energy level, which is number 2, but now we're in the p orbitals containing 6 electrons. And next is the third main energy level and the s orbital with 2 electrons in it. We can also write the abbreviated electron configuration of the magnesium atom. So here we have square brackets and we have neon, and this represents the electron configuration of a noble gas, in this case neon. So the noble gases will have full p sublevels. So up until here, the 1s2, 2s2, 2p6, that's the electron configuration of neon. And to save time, we write square brackets Ne, and then we have the 3s2. So that's the abbreviated electron configuration. Next, we look at the full electron configuration of the bromine atom. This time atomic number 35, 35 protons, so it must have 35 electrons too because it's the atom. So it's a bit longer this time. As usual, we start with the lowest energy orbital, which is the 1s2, then the 2s2, 2p6, 3s2, 3p6. Remember, the 4s2 fills before the 3d orbital, and then we end with 4p5 because bromine has 5 valence electrons in the 4p sublevel. And if you add these all together, it should give you 35. So next we look at the abbreviated electron configuration of the bromine atom. So the noble gas we're going to choose is up until 3p6, and that is argon. So square brackets Ar, that represents the electron configuration of argon. And then we start with 4s2, 3d10, and then 4p5. Chromium and copper. The reason we're looking at these two elements is because these are exceptions to the normal pattern of orbital filling. So let's start with copper, atomic number 29. The abbreviated electron configuration for the copper atom is square brackets Ar. This is the electron configuration of argon, 3d10, 4s1. Now previously we learned that because 4s orbitals are lower in energy than 3d orbitals, they fill first. Well, obviously here we have a half filled 4s orbital and a full 3d orbitals. The reason why copper has this electron configuration is because a full 3d sublevel is more stable. Next is chromium, atomic number 24. The abbreviated electron configuration for the chromium atom is square brackets Ar, argon, 3d5, 4s1. So again, we have a half-filled 4s orbital, and we also have a half-filled 3d orbitals too. And the reason for this exception is because the half-filled 3d sublevel is more stable. So these are two exceptions to the ordinary pattern of filling that we normally see, and these two have to be learned. Ions of the D block elements. Let's start by looking at manganese, atomic number 25. Here's the abbreviated electron configuration for the manganese atom, Ar3d5 4s2. Now, the abbreviated electron configuration for the Mn2 plus ion is Ar3d5. So that shows that when D block elements form ions, they lose their 4s electrons first, which you can see in this case. The first electrons to be lost are these 4s electrons here. Let's look at iron, atomic number 26. The abbreviated electron configuration for the iron atom is Ar3d6-4s2. Then we have the abbreviated electron configuration for the Fe2 plus ion, which is just Ar3d6. So again, you can see that the 4s electrons are lost before the 3d electrons. The next example is for the Fe3 plus. So we've lost these two 4s2 electrons, and we've also lost one 3d electron to give us Ar3d5. So 4s electrons are lost first. Orbital diagrams, or electrons in boxes. Let's start by looking at Hund's rule. Electrons fill degenerate orbitals. Degenerate orbitals are those orbitals which have the same energy. So electrons fill degenerate orbitals singularly before pairing up to minimize repulsion between electrons. So let's look at an example. The electron configuration for carbon is 1s2, 2s2, 2p2. So we can have these boxes and we can draw electrons in boxes, okay? So this is the 1s orbital, this is the 2s orbital, and these are the 2p orbitals. So we fill the lowest energy orbitals first, and we draw an electron as a straight line with a half head arrow. So we have one going up and one going down. They must have opposite spins. So this is the Pauli exclusion principle, which states that only two electrons can occupy an orbital and they must have opposite spins, okay? Then we move on to the higher energy orbital, which is the 2s. So we have two electrons in there, opposite spins. Now we're on to the 2p. Now according to Hund's rule, these electrons fill degenerate orbitals. These are degenerate orbitals of the same energy. So they fill singularly. So the common mistake is students do this. They put one there and one there. Now what's happening here is because we have these empty orbitals here, this is going to cause a lot of repulsion. So let me just erase these two, or this one. To minimize the repulsion, the electron goes into an empty orbital there. Okay? Let's look at another example. This is nitrogen, 1s2, 2s2, 2p3. So again, we have to give these the identity. So we've got a 1s orbital here, 2s orbital here, and a 2p here. So we start off with the lowest energy, opposite spins, two electrons in a box, 2s. Now again, Hund's rule, degenerate orbitals are filled singularly. So we have one here, and one here. Okay, so that's Hund's rule. Finally, the abbreviated orbital diagram for bromine. The abbreviated electron configuration is Ar4s2 3d10 4p5. And we can also write the abbreviated orbital diagram. So we start with square brackets and the noble gas. In this case, it's argon. And then we start with the 4s, and then the 3d orbitals, and then the 4p. So we start filling the lowest energy first, opposite spins, and we move on to the 3d orbitals. Now according to Hund's rule, how they'll fill is like this. Okay, they'll fill singularly, and then once these are full, we'll start pairing them up. Okay, and the same for 4p. So we need to put 5 electrons in the 4p sublevel. So there you go. This is the abbreviated orbital diagram for bromine.